Alright, gang, here we go. So this is Physics, Unit 5, Part 4. We're talking about the first law of thermodynamics. Should be fun. Okay, so I just wanted to start with this thing real quick just to give us an idea of practicing with our what we've done in the previous part here when we talked about heat and work, internal energy, so on and so forth, and just kind of get an idea of what those terms are, how they're applied, okay, that kind of thing here. Okay, so this here is a diagram of what's called a four-stroke cycle engine. Okay, and it's got four steps, right? Four strokes, right? So a downstroke, an upstroke, a downstroke, and an upstroke. And so this piston is going up and down, up and down, up and down. All right, up and down and up and down, and then it starts over. Okay, four strokes. All right. Okay, so the first step here is called the intake. So gas comes in, this little valve opens, a gas liquor fuel mixture comes in. Okay, the piston moves down and then spins back around, and then the piston moves back up. Compression. So that's your intake, your compression cycle. Okay, and then when it gets crammed in there, okay, it gets high pressure, the spark plug goes off, lights your fuel air mixture, and then you get combustion, and then your piston gets shoved down again, and then it comes back around and then moves back up, and then this side opens and exhausts out that spent fuel. Okay, so you got intake, compression, and combustion, exhaustion. All right, so this is the general four-stroke engine. So this is how most lawnmowers work, your cars work, so on and so forth. Very common engine design. Okay, so which is the work done on the gas? In which is the work done on the gas? All right, that's our first question. Well, let's ask ourselves, work done on the gas. So essentially, remember, work here is equal to pressure times the change in volume. Remember, we talked about how work, when you're doing work by a gas, that's the formula we can look at. All right, so work done on the gas. Well, are we, so we're really, the idea is, are we going to be looking at, we're going to look at a change in volume. Is that change in volume going to be the volume getting bigger or getting smaller? Okay, so if I'm doing work on a gas, well, you think about a balloon. If I'm going to squeeze that balloon down, I'm doing work on that gas, right? And so therefore, I'm looking for a smaller, I'm making a smaller area for or smaller volume, right? So any of these steps where it creates a smaller volume for the gas would be a work on the gas, right? So that would have to be compression here, right? So it gets in here, so it'd be so compression, right? Okay. Arguably, you could also say maybe exhaust too. Probably it just kind of depends on like how well it functions and how quickly that opens. There might be a little compression or a little bit of compression happening in your exhaust during that step. Ideally, no, but could happen. So you could say exhaust and probably be okay with that statement as well. All right, which was work done by the gas on the piston? Well, so which steps are causing the piston to move back because of the gas? Well, there's definitely this step, right? You're pushing, air's coming in, pushing down on the piston, right? So this is causing the piston to go down. So there's one. All right, so we'll say intake here. All right, what else is going on? So we've got, and then work done by the gas on the piston. Well, that'd have to be combustion, would be the other obvious one, right? Because combustion, because it's pushing this guy down, right? Which are adiabatic. So remember, adiabatic means that your Q equals 0, no heat change, okay? So which ones have absolutely no heat change? Well, it's going to be the ones that are in a closed system that happen very quickly. So it has to be compression and combustion, okay? You could make kind of an argument for the other two depending on it, but it's definitely these middle two, because this one, heat can come in and out with this new gas that's coming, and heat can come in and out with this gas that's escaping. But here, this compression and combustion, this is completely closed off, and it's happening very quickly. Remember, a process that happens very quickly is usually a sign of an adiabatic process. All right, which increases the internal energy of the gas? Well, increasing the internal energy, remember, internal energy is combined of your kinetic energy and your potential energy. All right, so in which cases are we doing either of those things? Well, let's see. When we're compressing it, we're increasing the potential energy of the gas. That internal energy is going up, so we'll say compression. Okay, and then combustion's obviously increasing the internal energy of the gas, so we'll say combustion. Okay. And then decreasing the internal energy of the gas, well, that would have to be exhaust, all right, as that gas leaves. Okay, and transfer heat in the environment also have to be exhaust, right? That just makes sense. Okay, so hopefully that gives you a decent idea of like how to go about setting yourself up for looking at these reactions, or looking at these kind of cycles, determining what's going on, what kind of process you might have that's happening, so on and so forth. All right, I'm going to move myself a little bit. All right, here we go. Okay, now we talked about before, remember we talked about this idea of mechanical energy, right? Mechanical energy. Mechanical energy was equal to the kinetic energy plus the potential energy. Okay, and so when a roller coaster goes, when we did some roller coaster problems or problems like that, we made the assumption that friction wasn't a factor, and so that our mechanical energy was conserved, right? That was kind of a bad assumption that we made, if you could say. So now we're going to be talking about, well, what would it actually look like if we did not assume mechanical energy was conserved? What would happen to that energy? Because the first law of thermodynamics pretty much states that energy cannot be created or destroyed. Okay, and so that energy had to go somewhere. All right. So in a frictionless roller coaster, or a non-real roller coaster, we simply convert our potential energy into kinetic energy, and the kinetic energy back into potential energy. We just kind of go up and down and up and down, right? So the potential energy, high potential, high kinetic, high potential again. Okay. In a real roller coaster, you have friction, so the mechanical energy is not conserved. You're going to be losing potential and kinetic energy over time, and that energy goes into increasing the internal energy, usually via friction. Okay, and wind resistance, vibration, sound, so on and so forth. That energy gets lost and increases the internal energy of the track and the wheels and the air around it. Okay, so we're going to do a little practice here and see what we can come up with. We've got this graph, and we're going to predict the appearance of the bar graphs at points C, D, and E. All right, so here at point A, the track's not moving, and it doesn't have any energy whatsoever. It's just chill. Okay, it's at 0 height. Okay. And so we're saying, okay, so it's got no kinetic energy, it's not moving, no potential energy, no internal energy. And then they hook it up to that chain thing that brings you up. I'm sure you all ridden roller coasters, and so they go, you roll forward, and then that chain picks you up to bring you up to, and you're like, as you go up to the very top of the hill, right? And it's just that kind of idea. And then now that we're at point B, we've got a little bit of internal energy now that we've got, we're up at the top of the hill, we've got potential energy. Now this part here, this is important, right? We put in any work here in order to get us up the uphill. Okay, this is work that we put in. Once we're at this point in our roller coaster, we're not putting in any more work into our roller coaster. That's it. Okay, so all the energy we have to get through the entire ride, we have to get from that bar. Okay, so as we look at our kinetic potential energy, okay, our total energy has to equal the total sum of all these three energies that are here. Okay, so at part C here, all right, so let's draw ourselves a little thing. So this will be part C, and we've got kinetic energy, potential energy, and internal energy. Okay. So part B, we had a lot of potential energy, no kinetic energy because we're just barely moving over the top, okay? And we go down the hill, right? So our kinetic energy, well, we're going to have some kinetic energy, right? It's going to be some good amount of kinetic energy because we just went down a hill. We're moving pretty good. Our potential energy is going to be lowered, right? Probably a little less than half of what it was before. Okay, because it's a little half the height, a little less than half the height that was before. And then the internal energy, well, what happens to the internal energy as we go? Well, the internal energy has to increase from here because it's going to gain even more internal energy as our ride goes on. So our internal energy is going to be, up higher than it was before. Okay, and these three, now please forgive me, but these three, technically these three bars should add up to be the same height as these three bars because that energy should be conserved. All right, now let's try again part D here. Whoa, why did I do that? All right, whatever. So D, okay, so we'll put D, and we have our kinetic energy, our potential energy, and our internal energy. Okay, so the kinetic energy, all right, what's our kinetic energy going to be like? Well, our kinetic energy should be pretty good, right? Kinetic energy should be pretty good because we're even farther down, right? And so our kinetic energy we should be moving pretty good, right? Kinetic energy should be like that. Potential energy should be exactly equal with A, so we should have absolutely no potential energy, right? And then our internal energy should be even higher because we've gone farther, right? So our internal energy should be something like that. Okay, and really this plus this should equal the same height as that plus that plus that, and that plus that plus that. All right, and then finally a part E, we're going to say part E is like right here. All right, just for grins. So this is part E. Okay, and then so we're going to do this. All right, we have kinetic energy, potential energy, and internal energy. All right, so the kinetic energy, we're not going to be moving too terribly fast, right? We're going to be like something like this, okay? Our potential energy is going to have to be pretty high, right? A little higher than C's was, but not as high as B's. Okay, so we're going to be like this, okay? All right, and then the internal energy would have to be even higher, right? So really, the kinetic energy would probably be even lower than what we drew it, right? And I know that because these two heights have to be equal to one another, all three of those added together. So that kind of gives you an idea how your kinetic and your potential energy lose over time to internal energy. So you're eventually, you'd run out of steam and your cart would get stuck somewhere and you wouldn't be able to keep going like this forever because your kinetic and potential energy would eventually run out, turn into internal energy. Okay, and this leads us to our first law of thermodynamics. First law of thermodynamics that we're working with here states that the internal energy, or delta U, okay, is equal to the Q minus W, or the energy transferred to or from the system as heat minus the energy transferred to or from the system as work. Okay, Q minus W. All right, now, a couple of signs you need to pay attention to. If energy is added to the system as heat, our Q is positive. Okay, so we'll just put in a little plus sign here. If energy is removed from the system as heat, we put in a little negative. Okay, if no energy is transferred, then Q equals 0. We'll put a little parenthesis and we'll say, oh, this is an adiabatic system. Okay. All right. If work is positive, work was done on the system, so our gas expanded. All right, so this is positive. All right, if work was done on the system, our gas compressed, this would be negative work. Okay. And then if no work was done whatsoever, work equals 0. Okay, and the only system process we talked about where work equals 0, this was the isothermal process. All right, so let's do a practice problem here, okay? Gas is trapped in a small metal cylinder with a movable piston and is submerged in a large amount of ice water. The initial temperature of the gas is 0 degrees Celsius. A total of 1,200 joules of work is done on the gas by a force that slowly pushes the piston inward. Okay? All right. So, is this process isothermal, adiabatic, or isovolumetric? Well, we know it can't be isovolumetric because the piston's moving, so there's change in volume, so that kicks that guy right out. We also know it can't be adiabatic because this isn't going to happen very quick, right? There's going to be lots of heat moving across it, so it has to be isothermal. Okay, and we also know it's isothermal because the gas started at 0 degrees Celsius, and you're putting in a large amount of ice water. Well, the temperature of ice water is 0 degrees Celsius. That's kind of the point, right? Water freezes at 0 degrees Celsius. So if you have ice water, that's water and ice mixed, it has to be sitting at 0 degrees Celsius, okay? So it's isothermal, so your temperature is not going to be changing, okay? Now, one thing to keep track of, remember, in isothermal, this means that your work is equal to 0, all right? No, not your work, your delta U. I'm so sorry. I was like, that doesn't sound right at all. It's because it's not right at all. Okay, your delta. All right, let's see. So we cross out adiabatic. Okay, so this means your delta U is equal to 0. All right, now it says how much energy is transferred as heat. Okay, so this is really asking us for Q. Okay, between the gas and the ice water. Okay, so we know that delta U is equal to Q minus W. That's the first law of thermodynamics. All right, delta U in this case is equal to 0, so this is saying 0 is equal to Q minus W. All right. Well, so then we can just really rearrange this. So Q is equal to W, right? And so we know that a total of 1,200 joules of work was done, so Q is equal to 1,200 joules. Pretty slick, okay? Pretty slick. And this says how much ice would melt as a result of this heat transfer. Well, we know the heat transfer was 1,200 joules. Okay, so we need the latent heat of fusion. Remember talking about that a couple of videos ago? Latent heat of fusion of water. Well, the latent heat of fusion of water is equal to 333.55 joules per gram. Okay, so we're going to use this as our ratio. So we're going to convert 1,200 joules. We're going to use dimensional analysis. We're going to put joules in the bottom, grams at the top, and it says right here it's 333.55 joules for every 1 gram. All right, and so we'll take 1,200 divided by 333.55, and we get 3.6 grams of ice. That's how much. Okay. Heat engines. Okay, heat engines are cyclic processes, meaning they work and go and they end at the same temperature that they start with. Okay, so a fluid returns to its initial temperature and pressure. All right, so this means your delta U equals 0, which makes it really nice. So that means our heat applied gets turned into work. Okay, net heat equals net work, which is really nice. Okay, so essentially heat engines take heat from a substance at a high temperature and use that energy to do some sort of work on the next bullet at a lower temperature. Okay, internal combustion, so that 4-stroke cycle, that engine that we looked at the beginning, that was a heat engine, right? It used heat to do work. Okay, so hot gases do work on the piston and they're expelled at a lower temperature. In class, I probably showed you either a Stirling engine or something similar to it, where we used a heat source in order to make the wheel turn the piston move up and down, and that was just a heat engine. Steam engines are really just heat engines. Okay, so you've seen steam engines with cars or with from locomotives. Hopefully your car doesn't run on a steam engine anymore. Okay, that's pretty old school. That's steampunk. All right. Anyway, so you've got your steam goes in, turns your turbine, engine turns it into gas, and so in this case the steam would turn the piston and would turn the wheels on the car, and you get the chugga with the pistons going back and forth, and that's essentially what's going on. And after the steam does work, the steam has to cool down because it's lost its energy, and it gets expelled at a lower temperature than it was before. Okay, and so here's the general idea. Hot heat comes in at a high temperature, and a high Q comes in, and that high Q comes in and does work, and that work is related to QH minus QC, right? And then the cool comes out as QC, and you're at this new lower, cooler temperature. Okay. Refrigerators are also heat engines, but they work backwards. Okay, so instead of taking heat and doing work, they use the idea of stealing heat in order to do work. It's kind of funky. All right, so essentially what happens in a refrigerator is that heat moves from a lower temperature, okay, inside the fridge to a higher temperature outside. And in order to make this happen, we do work. Okay, and air conditioning systems follow the same principle. Okay, so in your fridge, essentially what you've got is you've got this idea. Okay, you've got what's called an expander. Okay, and an expanders a lot of times are like a coil system. Okay, a really, really thin coil system. So your refrigerant will go into this coil system here, okay, and get expanded. And when it's expanded, it cools down, right? Anything that gets expanded very, very quickly is going to cool down. Okay, and so you get this really, really cold refrigerant that comes out, and then that thing there goes through your fridge. Okay, so this is our fridge. We'll just say this is our fridge. Bear with me. And this is going to go through your fridge and is going to do coils inside your fridge. Okay, and everybody's fridge is a little bit different. Mine's ugly. So, and then, but while it's in here, because this was cool when it entered, it's colder than the temperature inside the fridge. And so heat from the fridge is going to, it's going to try to reach thermal equilibrium while it's in there. So heat from the fridge is going to try to enter into the refrigerant and try to reach the same temperature. So the refrigerant starts to warm up because of the heat from the fridge. And then it travels back out of your fridge, right? It coils around in there, around the walls, and sometimes through some of the shelves. It kind of depends. Different fridges do different things. Anyway, and then it exits the fridge, comes out here, and then it enters what's called a compressor. And the compressor is a little machine. And this is the sound you hear in your fridge where it goes and it kind of turns on. That's the compressor of the fridge going. And the compressor, so right now you've just got a high temperature gas right here. All right. What this guy that got up to a higher temperature, but not terribly high, from being in there and reach thermal equilibrium with your fridge. Okay, it hits the compressor. The compressor is going to compress the bejeebies out of this guy, and then the high pressure gas is going to come out here. Okay, and now you've got a high pressure gas right here, and then it's going to start doing more coils, and because now this is at a higher temperature than the outside air, then the heat from here is going to leave. Okay. And so your heat from your refrigerant is going to leave, and then this guy goes back in there, so on and so forth. Bob's your uncle. Okay, so that's kind of the general idea of how a refrigerator works. This video here does a really good job explaining it. There's lots of really good videos online of people explaining exactly how refrigerators work and air conditioners and stuff like that thermodynamically. But that's it for part 4. You did it. First law of thermodynamics. Do your practice problems. Woohoo. Let me know if you have any questions. I'll see you on the flip side.